Hello friends, welcome to my YouTube channel Ik Onkar Coding. Today in this session we discuss the searching techniques to search an element in an array. Basically we have two techniques to search an element in array. One is linear search, another one is binary search. So in today's session we discuss both searching techniques with time complexities. And then we discuss which technique is more efficient as compared to the other technique. So now start with the linear search. Linear search is also called sequential search. In this we compare the searching element with every element of the array. Suppose we have an array in this example we have 7 elements in the array. First element is 23, then 13, 21, 15, 38, 45 and 70. Now suppose we have to search the element x that have the value 38 in this array. So in linear search we start the comparison with the starting element of the array. So in this we compare this searching element x with the starting element of the array. So 38 match with 23, no, move to the next element. 38 matched with 13, no, move to the next element. 38 match with 21, no, move to the next element. 38 match with 15, no, move to the next element. 38 match with 38, yes, here element is found. Now if the element is found in the array, we have to display the index where the element is found. So after this we display the index of the array, and if element is not found then we display the null value. So now we discuss the code for the linear search, and after that we also discuss the time complexity for the linear search. Now I discuss by example in coding languages. So first we include the IOStream header file, then standard packages, then we include the main function. After this we declare an array of size 20. Here n represent the number of elements in the array, I represent the index of the array, x represent the searching element that you have to search in this array A. So first we display the message enter number of elements. So first we enter the value of n. After this we enter the elements in the array. So here in this I use for loop and I start from 0, and here I give the condition I less than n and I plus plus. I is updated by plus plus operator, and then here I use cin object, cin a of I. So this loop is executed how many times? N times. Okay, suppose here you input the value of n as 5. Okay, so it means here number of elements are 5, and now this for loop is executed how many times? This for loop is executed 5 times, and 5 elements are entered in this array A. After this, after entering the elements in the array, now we enter the element that you want to search. So we display the message enter element to search. After this we enter the value of x. Suppose here you enter the value of x as uh, 50. Okay, suppose you enter the value of x as 50. Okay, that you search and that you search in this array A. Now for performing the comparison, now I start the comparison. For comparing the searching element with every element of the array, we implement a for loop, and first we compare with the starting element of the array. So I start the for loop with 0 index, with 0. Okay, I write here I is equal to 0, and then I less than n, because the index of the array goes up to n minus 1, because array index start from 0 to n minus 1 means n elements. and then I is updated. Now for comparing, here I implement the if structure. Here I write the condition if a of I double equal to x, if the searching element is equal to a of I, then we display the message element is found at index. This is just a message, and then we display the value of I. And if the element is found in the array, it means now there is no need to move to the next iteration. So that's why here I implement the break statement. When this condition value is to true, it will display the message that element is found at index I, and after that break is encountered, and when break is encountered, control jump out of the if structure or for loop. The thing is, control jump out of the for loop, control jump out of the for loop. Okay, because break is not compatible with alone if else. If you write alone if else on a compiler, and if you include the break statement inside alone if else, compiler give you error because break is not compatible with alone if else. So we have to use here for loop. Okay, the thing is, break is compatible with the switch structure, and break is also compatible with the looping structures. And when break is encountered, then control jump out of the for loop and next iteration is not executed in that case. So here I implement break because there is no need to move to the next iteration if the element is found. And after this, here I write the condition if I double equal to n. If I is updated up to n, if this condition value is true, it means element is not found in the array. Okay, now I first we discuss the previous code here. Okay, so first you input the value of n as 5. Okay, after this, suppose you enter the value of you enter the element here. Suppose first element you enter here 10, second element you enter here 20, third element you enter here 30, fourth element you enter here 40, and fifth element you enter here 50. Okay, suppose these 5 elements you entered in the array. Okay, and first element have the index 0, second element have the index 1, third element have the index 2, fourth element have the index 3, fifth element have the index 4. Okay, now here your searching element is 50. Now I is equal to 0, 0 less than 5 because n has the value 5, 0 less than 5, condition true. Okay, here condition values to true, control go inside the for loop. Now x has a value 50. Now a of I means a of 0, a of 0 is 10, so 10 double equal to 50, condition false. So after this, control jump out of the if structure here. After this there is no statement, so I is updated. Now I becomes 1, 1 less than 5, again condition true. Now we compare. Now a of I has a value 20, 20 double equal to 50, condition value is to false. So if this condition value is to false, control jump out of the if structure here, and after this there is no statement, then I is again updated. I becomes here 2. Now we compare a of 2. A of 2 has a value 30. A of 2 has a value 30 here. Okay, 30 double equal to 50, condition values to false. Then control jump out of the if structure, again I is updated, I becomes 3. Now we compare a of 3. A of 3 has a value 40. 40 double equal to 50, again condition values to false, control go here. After this I is updated, I becomes 4, 4 less than 5, condition true. Now a of 4 is 50. 50 double equal to 50, condition values to true, control go inside the if structure, and here it will display element is found at index I. Now here what is the value of I? Now here I has a value 4. Okay, so here I has a value 4, it will display the value 4 for I variable. After this, break is encountered. When break is encountered, control jump out of the for loop. And after this, now we check this condition. If I double equal to n, now last value of I is 4 and n has a value 5, 4 double equal to 5, condition false. So this statement is not executed in this case. Okay, and after this, return 0 and program is ended. Okay, I hope you clear about the uh, technique of the linear search. Okay, so this is the output of the above program. So first we enter the number of elements. So here I enter the elements, number of elements as 5. After this, we enter the elements in the array. So 10, 20, 30, 40 and 50 are the elements in the array. So after this, you enter the element that you want to search, that is 50, and after this it will display the message that element is found at index 4. Okay, now tell me how many comparisons you have performed in this problem. In this example, how many comparisons you performed? So the thing is, here how many comparisons you performed. I start from 0, I goes until 4. So 0 to 4, how many times? 5 times. So it means 5 times this loop is executed, and 5 times you compare this condition. Okay, so and 5 n also has a value 5 here. Okay, so the number of comparisons here are 5 in this case. Okay, so the thing is, time complexity of any program and time complexity of any algorithm is purely depend upon the number of comparisons that you performed in that problem. So here n has a value 5, that's why here 5 comparisons have been performed. So the time complexity of this technique is big O of n. So if you analyze the time complexity of a linear search algorithm, okay, then it becomes big O of n. Okay, now n is the number of elements in the array. Okay, if the thing is, if we have an array of 100 elements, if we have an array of 100 elements and has a value 100 in this case, and your element is the searching element that you want to search in an array, and that element is placed at the last position, that is 99. If n has a value 100, the index goes from 0 to 99, and your searching element is placed at position 99. In that case, how many comparisons you performed? In that case, we perform 100 comparisons. 0 to 99, 0 to 99 becomes 100 comparisons, and also has a value 100. So here the complexity becomes big O of n. Okay, so basically we have three cases. We have three cases to find the complexities. First is the best case. When the best case will happen? Best case is happen when the searching element is at the first position, when the element is found at the very first position. In that case, how many comparisons you performed? In that case, you performed only one comparison. So by performing first comparison, our element is found. So that's why here the complexity becomes big O of 1. And in this case, what is the worst case complexity? So if your element is placed at n minus 1th position, and that is the worst case. In that case, the complexity becomes big O of n. Okay, now the thing is, how you find the average case complexities. Now for finding the average case, the now the thing is how we find the average case complexity of any program or any algorithm. Now for finding the average case complexity, the rule is you have to find out the average of, you have to find the average of average of number of comparison of number of comparisons of all cases, okay. Now if your element is plays at first position, in that case how many comparisons you performed? In that case you perform only single comparison. If your element is found at second position, how many comparisons you performed? You performed in that case two comparison. After this, if your element is placed at third position, in that case how many comparisons you performed? You performed in that case three comparison, and up to so on. If your element is placed at nth position or n minus 1th position, in that case we performed how many comparisons? N minus 1 comparison, okay. And if you do the now how many comparisons are here? How many cases are here? We have total how many cases? We have total uh, n cases, okay. And uh, what is the formula for finding the sum of this series? The formula is n into n plus 1. Yeah, n is into n minus 1 divided by 2, okay. So it becomes divided by n, okay. So this n is divided by this n, okay. So again it becomes big O of, it becomes n by 2 plus 1 by 2, okay. Now in algorithms we assume that n has very large value. We assume n has very large value. So n by 2 becomes, again it becomes n plus 0 0.5, okay. So completely it becomes n, okay, because if n has very large value, if you add 0 0.5, it again becomes n. So big O of n is the total complexity for the average case, okay. So I hope all of you clear about the average case, okay. So now we move to the binary search. So now we start the next technique, that is binary search. Now the thing is, in this approach we divide the array into two halves. Now in this array is divided into equivalent two equivalent halves, okay, by finding the middle element of the array. Now the pre-specified condition for implementing the binary search is your array is already in the your array should be in the sorted order, okay. If your array is not in the sorted order, it means we are not able to apply the binary search technique. So this is the pre condition for applying the binary search, that is your array elements are already in the sorted order, okay. Now we discuss by example, okay. Suppose we have an array of 10 elements. So index start from 0, it goes until 9, okay. Now elements in this array are 10, 20, 30 and up to 100, okay. If you analyze, all the elements in this array are in the sorted order, okay. Now here we find the middle element of the array. How we, the thing is how we divide this complete array into two halves. The thing is by finding the middle term, okay. Now there is one formula for finding the middle term in binary search, that is m is equal to f plus l divided by 2. Now f represents the first index that has a value 0, so I assume here f has a value 0, and last index is n, so l represents the last index and l has a value n. Now this is the formula, m is equal to f plus l divided by 2. So in this case m become 0 plus 9 divided by 2, so it becomes if you take it as 4.5, but all these first index, last index and middle term are of int type, so it becomes 4. So 4 is the middle index, okay. Now suppose you want to search the element x 100 in this array. Okay, so the thing is, in this, every time we compare the searching element x with the middle element of the array. Okay, and we by performing first comparison, the complete array is divided into two halves. Okay, and after that we after comparing with the middle element, we analyze in which half our element is existed, in the first half or in the second half. Okay, so for this, um, we discuss one pseudocode. This is our pseudocode. Okay, so initially at the starting time, f has a value 0, l has a value 9. Okay, so in this case, m is calculated as 4 by using the formula f plus l divided by 2. Okay, now m has a value 4, and what is the value of a of 4? A of 4 has a value 50, if you remember. Okay, just wait. Here a of 4, this is our middle element, this is our middle element, a of 4. Okay, so by finding this as middle element, your array is divided into two halves. This is our first half and this is our second half. Okay, now we compare the searching element x. We compare searching element x, that is 100, with a of m. What is the value of a of m? A of m means a of 4. A of 4 has a value 50. Here a of 4 has the value 50. Okay, so now we discuss this. Now we compare a of m. A of m means a of 4. Now 50 double equal to 100, condition true or false? Condition values to false, so control go in the else part. Now a of m. Now what is the value of a of m? A of m has a value 50. 50 is less than 100, condition values to true. If your middle element is less than your searching element, it means your element is in the first half or in the second half. It means your element is in the second half, because your searching element is greater than middle element of the array. Okay, I hope now you understood better why there is one condition that your array elements must be in the sorted order. Okay, so here if your element is in the second half, now we update the value of f, that is m plus 1. In that case, we update the value of f as m plus 1. Okay, so here now m has a value 4. Here m has the value 4. Okay, in this case m has the value 4. Okay, it means your searching element is in the second half. Okay, so now f becomes is equal to m plus 1. If your element is in the second half, if your element is in the second half, it means there is no need to update the value of l. There is no need to update the value of l. Now we update the value of f. We update the value of the first index. Now first index becomes f is equal to m plus 1. Now first index becomes m has a value 4. 4 plus 1 is equal to 5. So now first index becomes 5. Now we search the element is only in this second half. Okay, from 5 to 9. Now in this case, in the second iteration, now f becomes 5, l become 9. Now again we calculate the middle element. 5 plus 9 divided by 2. 5 plus 9, 9 plus 5, it becomes 14. 14 divided by 2, that is 7. 14 divided by 2, 7. Now this is our middle element. Now 80 is our middle element. Now again 80, that is middle element is 80. A of m double equal to x, condition true or false? This condition again values to false, because your middle element is not the searching element. Okay, so now we analyze that your a of m is less than x, it means again your element is in the second half. If your element is in the second half, now in the third iteration, what I do now in the third iteration, here f becomes m plus 1. Now what is the value of m? In the last iteration m has a value 7. Now f becomes 7 plus 1 is equal to 8. L is equal to 9. L is not updated. Now m is equal to 8 plus 9. 8 plus 9 divided by 2. 8 plus 9 is 17. 17 divided by 2, that is 8. Okay. Now middle element becomes 8. Now a of 8 has a value 90. A of 8 has a value 90. So again, now we move to the, now middle element is not the searching element. Okay. So now we move to the fourth iteration. Now in the fourth iteration, what is the value of f? F has a value, again f becomes m plus 1. What is the last value of m? Last value of m is 8. So 8 plus 1, 8 plus 1 is 9. And L is not updated. L is again 9. So middle element is equal to 9 plus 9 divided by 2. So 9 plus 9 divided by 2, it becomes 9. Okay. So now middle element becomes 9. Now we compare a of m with searching element x. Now a of 9 is equal to 100. That is, your element is found. Okay. So I hope you clear better. Okay. So now thing is, if your a of m is double equal to x, then we display that element is found at index m. Otherwise we move to the else part, and here we evaluate the condition. If a of m is less than x, it means your element is in the second half. If this condition value is to false, then it means your element is in the first half. If your element is in the first half, then there is no need to update the value of f. Now we only update the value of L. Now L becomes m minus 1 in that case. Okay. So now we discuss this thing by example. Now we discuss all this thing by the code. Okay. So first we include the iostream header file, then we include the standard packages, then we include the main function. Okay. After this we declare an array A of size 20. After this we include I represent the index of the array and represent the number of elements in the array. F represent the first index, L represent the last index, M represent the middle index, X represent the searching element. X represent the element that you want to search in the array. So first we enter the value of n. Suppose here you enter the value of n as 10. After this you enter the elements in the array. This is just a message that will display as such on the output screen. After this, using this for loop, I start from 0, I less than n, I plus plus. Now your loop start from 0, it goes until n minus 1. So n times this loop is executed, and you entered how many elements? N elements. Now n has a value 10, so 10 elements are entered. 10, 20, 30, 40, 50, 60, 70, 80, 90 and 100. These 10 values are entered by the user, and all elements are already in the sorted order. Okay. After this we enter the value of x, that the element you want to search in an array. So first we display the message, enter the element to search, then we enter the value of x. So here you enter the value of x as 100. After this, now I initialize f with value 0, because your first index is always 0, last index is always n minus 1. Now we calculate the value of the middle element. So f, the formula for for calculating middle element is f plus L divided by 2. So f first index plus last index divided by 2. Okay. So using this formula we calculate the middle element. Now after this we implement a while loop. Okay. Here in the while loop I give the condition first less than equal to L. Okay. So if you analyze binary search technique, the thing is, in binary search first index is always less than and equal to x. If your first index is greater than equal to L, it means your element is not existed in the array. Okay, so if your element is existed in the array, then first index is always less than equal to the last index. Okay, so here I implement this condition, because if your first index is less than equal to x, in that case only we do the comparisons here. Okay, if your first index is not less than L, it means first index is greater than L, it means there is no need to enter in the for loop. There is no need to perform any comparison here. There is no need to compare the middle element with the searching element of the array. So if your first is the thing is, if your first index is greater than L, if in any case your first index is greater than L, it means element is not found in the array. Okay, so I hope you clear why the first index is always less than equal to the last index. Okay, so for binary search technique, first index is always less than equal to L. Okay, now we compare. Now here again I implement the same condition here. If a of m is less than x, if your middle element is less than the searching element, if your searching element is greater than the middle element, it means your element is in the second half. If your element is in the second half, then we update the value of f as m plus 1. Okay, if this condition value is to false, control go to the else part. If middle element is middle element is equal to the searching element, then we display element is found at index m and break is encountered, because in that case there is no need to move to the next iteration. So that's why I implement here break structure. And when break statement is implemented, control jump out of the if structure or while loop. The thing is, control jump out of the while loop, because break is not compatible with alone if else. And if this condition value is to false, then control go to the else part. It means your element is in the first half. If your element is in the first half, then there is no need to update the value of f. Now we update the value of L as m minus 1. Okay, after this statement belongs to the else part. Okay, and this is this middle element. Here I include the formula of middle element. M is equal to f plus L divided by 2, because here I implement here this is for the updation. Okay, because we calculate the value of the middle element only if f is less than equal to L. In that case only, we only calculate the value of the middle element, that is f plus L divided by 2. Here your while loop is completed. Okay, here your while loop is completed. While loop is started here, and and here after the else part we calculate the middle element, and here your while statement is completed. And if after this we write the condition here, if f is greater than L, then element is not found, and after this your main function is ended. Okay, so I hope you clear about the approach of the binary search. Okay, the thing is, if your the thing is, if your searching element is equal to the exactly equal to the middle element, then element is found at index m. Otherwise, if your element is in the second half, then we update the value of f as m plus 1. If your element is in the first half, then we update the value of L as m minus 1 in that case only. So after, I hope all of you clear about this. And now we discuss the time complexity for the binary search. Now we discuss the time complexity of the binary search. So the thing is, the time complexity of the binary search is big O of log n. Big O of log n. Okay, how big of log n is the complexity for the binary search? The thing is, first we discuss how to calculate the log. Okay, now the thing is, log base 10, 100 is equal to 2. Why? Because 10 raised to power 2 is equal to 100. Okay, and log base 10,000 is equal to 3, because 10 raised to power 3 is 100, sorry, 1000. Okay, in a similar way, log base 2 8 is 3, because 2 raised to power 3 is equal to 8. In a similar way, log base to 16 is 4, because 2 raised to power 4 is 16. In a, in a similar way, log base to 32, log base to 32 is always 5. Okay, in a similar way, you can calculate the you can calculate the log of any value. Okay, so the thing is, in the example that we discussed in this binary search technique, in that technique, the number of the value of n here is 10. Okay, and how many iterations you performed? If you remember, here we performed 4 iterations. Here we performed 4 iterations. Okay, I will show you. Just I will show you. Yes, this is the case. So in the first iteration, this is the first iteration. In the first iteration, m has a value 4. In the second iteration, m has a value 7. In the third iteration, m has a value 8. And in the fourth iteration, m has a value 9. And when the middle element become 9, and your ninth element is 100, that is your searching element. So here, how many iterations we performed? We performed four iterations. Okay, so how many times, the thing is, how many times we calculate the middle element? We calculate the middle element 4 times. So that's why now the thing is, log base to 10, log base to 10 is, the thing is, log base to 8 is 3, and log base to 16 is 4. The thing is, log base to 10 is in the middle of 3 to 4. Log base to 10 is in the middle of 3 to 4, and we take seal value. So it, now I take this as 4, because it in actual it becomes 3 point something, 3.45 something. Okay, and I take seal value, so it becomes 4. So that's why here the complexity, the time complexity for the binary search technique is log n. Okay, now the best case complexity is big O of 1. If and in the very first comparison, when you in the very first iteration, when you calculate the middle element, and your middle element is the searching element, so in that case, how many iterations you perform? You perform only 1 iteration. How many times you calculate the middle element? You calculate the middle element only 1 time. So that's why the complexity becomes big O of 1. And average case and worst case complexity is same in case of binary search, so that is the log n. Okay, that is the case we discussed in the previous example. I hope now you clear. I hope now you clear both techniques of linear search and binary search. Okay, thanks for watching my video, and kindly like, comment, share, and subscribe my channel. Okay, thank you all.